Hi guys, so let's start. It's 10 past 10. My name is Raid Sakur, and I'm the last in list of your course instructors this semester. Before I start, maybe just talk about the logistics. So just by the show of hands, can I see how many of you have already done assignment 1? Are you done with it? How many of you have, oh, you're done? Yeah? Okay, you don't have to, yeah, your classmate's gonna hate you, so yeah, it's okay. How many of you have at least started? Okay, great, awesome. So yeah, so it's due on February 9th, and please, it gets really, try to get started early. And if you have any questions, the TAs are there, and we have office hours. Try to utilize the office hours as well. Assignment 2 will be released a day after assignment 1 is due. And there's a reading week break on February 19th to 23rd. And final exam dates, it's not planned yet. When the date is finalized, we'll let you know. And one thing I wanted to mention is the lecture feedback. Please, I'd really appreciate any feedback if you have. It's anonymous, and it really helps us to improve the quality of the materials that we give you. Okay, let's get started. So this is the plan for today's lecture. We're going to talk about neural language models for 2 sessions, today and next Monday. Today we'll be talking about word level representations, word to vec, skip drum, and continuous bag of words. We'll start on neural language models. And then on Monday, we'll cover RNNs, LSTMs, and contextual word embeddings. And after that, we'll have machine translation. We'll segue into using those language models to actually doing a downstream task like machine translation. This year, we'll focus a little bit more on transformers. So hopefully in the assignment, you'll get to do some hands-down coding of using transformers to do machine translation. And okay, so this year I just wanted to give a brief historical background before I get started on neural language models. So as you can see in the diagram, or as you already know, that what we're going to talk about is nothing new. That's it's been there for a while, and with different monikers over the years. And if any of you are interested in the history of ML history, then on the course website there is a Lighthill report that if you want, you can read about it. That sort of gives you a background about the so-called first AI winter, which happened circa 1970 around that time because of this Lighthill report and a paper by, I think, Minsky, that actually really suppressed the ML or AI research for a while. Anyway, moving on. So what are artificial neural networks? So essentially it's kind of inspired from neurobiology. You can think of it as many inputs coming through the dendrites, and you have one output axon, and the nucleus fires or sends an electrical signal along the axon, given input from other neurons. So learning occurs in the synapses, and that connect the neurons either by amplifying or attenuating the signals. So if we juxtapose that with perceptron or an artificial neuron, we can see that analogical scenario is happening over here, where you have a bunch of inputs or activations coming, and in the center you're calculating the total weight, and if it's above a certain threshold, you're saying that, okay, let's fire. If it's below that, then you're suppressing that signal. So the output is determined by what we call activation functions, which is nonlinear functions of the weighted input. And this activation function comes in many flavors. Here on the bottom left, you can see what is called a hyperbolic tan activation function, which suppresses the input between -1 and 1. And on the bottom right, you can see a sigmoid activation function, which suppresses the input between 0 to 1. And one quality that we look for sigmoid functions or this activation functions is being able to take derivatives easily. And we'll see why being able to take derivatives easily is important in a few slides. So currently the de facto activation unit, or the most popular activation units we see in practice is called rectified linear units, or ReLU. As you can see on the bottom right, it's, the function is designated by the blue line, and it's like a max function. And this is very, this has several advantages, applied advantages like, sparse activation, meaning that, if the signal is less than what we desire, instead of think of a very low value, we just like designate it as 0, right? Otherwise, this sort of helps with the limiting or vanishing gradient problems, and it's also it's good for efficient computation. There are also many flavors of it, like smooth approximation, like soft plus, and which also has a smooth derivative. Now, as I was saying that, why do we need derivatives, or why being able to take derivatives is important? So this is where we look into how the learning is happening in perceptron. So we want to adjust the weights in proportion to the error. So we have, if in a supervised learning in a supervised learning setting, we have the desired y, the actual output s, and we take a derivative that allows us to, assign blame proportionally, and allows us to, backpropagate the error in order to adjust the weights. So what would be a drawback of a single perceptron like this? So if you think about representation, so we can use this single perceptron to represent logical functions like AND or. But on the right-hand side, if you look at an XOR function, there's no way to linearly separate the XOR function. So a single perceptron cannot, satisfy a simple function like XOR. And this, what I was alluded to earlier at the beginning of the lecture, the first AI winter, this was presented as a big deal in a Minsky and Papert paper. I think it came out in 1969, and then later was, came out in the Lighthill report, where among many other deficiencies, this deficiency of not being able to represent simple functions like XOR using a single perceptron was seen as a really sort of detrimental effect on the whole subsequent research on using artificial perceptrons. At the time, though, Minsky and Papert and the people actually knew that this problem does not translate if we use multilayer perceptrons. But at that time, from a computational perspective, the use of multi-layer perceptron was so implausible or infeasible that didn't really come into the paper, or that didn't have much weight in the discussion. So this limitation can be circumvented if we actually use multi-layer perceptrons. So if we layer up these perceptrons, we can represent complex functions, and we'll be designating this as MLP going forward. And here, the inputs are passed to the first layer of a multi-layer perceptron, and they are propagated up the chain, and then you get the output layer with some output presentation. And as it turns out that MLPs are quite robust to noise and can be trained specifically using backpropagation and those techniques to reduce error. So as a simple example, here, we can classify a whole bunch of image data set using layers of MLP. So you can basically rasterize or vectorize each of these images and then feed it to an MLP and get the sort of representation in the output layer, and then you can do whatever task you want to do. Let's say if it's a classification task, then you'd backpropagate the losses and train your model in such. So for example, a picture like this, where you can classify this output layer that, okay, so this is a cat, and so on. So for example, if you're trying to, let's say, classify the emotions conveyed in a whole bunch of pictures of human faces, you can say that, oh, okay, so you can assign whatever your label is, you can train a network like that. And the hidden representation of this, whatever label is sort of learned in the hidden layers over here. Now, how can we apply this technique to our purposes, that is, in language, or how do we represent word? So as many of you already know, the simplest way to do this is what we call one-hot representation. So you have a whole bunch of words. Let's say you have 100K unique words. and you have a big matrix where you assign 1 to each word. So here, let's say we want to represent lugubrious in this way, so we'll just assign 1, and every other column is 0. So we have a one-hot representation. Now, in your assignment, I think you already got exposed to what we call like dense feature, where you have a word feature representation for psychology-based features like cheerful, emotional, tone, and etc. So can we instead of doing one-hot encoding, can we do denser representation, and what does it give us? What is the pros and cons of it? So let's take a look. Okay, so a famous historical saying goes by J.R. Firth that you shall know a word by the company it keeps. So and this idea sort of inspired a lot of early semantic representation that we use today. So here, for example, going with our running example, the word lugubrious. And here what we're trying to do is that we want to look at its surrounding words, both after it and before it, and we'll try to predict what the center word will be. So if we have the words been, feeling, and then let's say a dash, and then all day, so then we're trying to predict the center word lugubrious. And how can we do that? So this is the idea is conveyed in the technique called continuous bag of words, or CBOW model. So how do we do this? So in order to sort of, for a pedagogical reason, I'm just going to go through an example with using just one word, okay? So here in this picture, just first thing, the assumption is that we're just doing one word, okay? So let's say the input word is feeling, and we're trying to predict the output word. With that, the way it works is that you have some representation for feeling. So if you go with one-hot encoding, then it'll be just like all zeros, but just one for feeling. And let's say your W input is like a matrix of all the words in your vocabulary, right? So here, I think D is 100K, is like D is the size of your vocabulary. So you have 100K words, and each word is being represented by H, some feature size is H, okay? So, and then if you multiply that word feeling with this input word embedding, you get the representation for the word VW, which is the input word representation of feeling, okay? So if you think about it, if it's just a one-hot encoding, if you do X transpose by WT, this actually just gives you one row of the embedding matrix, right? Like whatever the one corresponds to, you're just reading that off, if you think about it. And then you use this input word embedding, and then on the other side, you have the output word embeddings, where you have like another output word embeddings embedding matrix W0 or WO, and it's giving you the corresponding column of the word that you think is the next word, okay? So in vector representation forms, that would be like VW, where V is the capital W here for the output, and here we get the output embedding matrix multiplied by whatever the output word we think our predicting is. And then we're just basically like learning. We're trying to maximize. If you look at the bottom right, actually give me a sec. Anyway, maybe it will work. Okay, can you see the pointer? Okay, I should have done this earlier. But anyway, so if you look at the bottom right over here, then you can see that what we're trying to maximize is, we're interested in the probability of the output word given the input word. And we do, this is the softmax function, and this is what we're interested in, okay? So this is the basic principle. Now this is for just one word, but when you do CBOW, or continuous bag of words, you have like words, preceding it and after it as well. But this is just an example using just one word. So what happens, let's say the context is longer. Let's say we have a C words context. So it's basically the same idea, but we just average the embeddings of all the context words. So before we had one word, now let's say we have like 3 words, and then here we can see that we're taking the embeddings of each of those context words, and then we're doing an average, and then again, is this exactly the same thing? Yeah, question?
In which situations do you average it versus concatenate?
Yeah, so in the, yes, so when you have multiple contexts, so for example here, if I give you been feeling all day, right? So you have 4 context words, right? And in that case, what you do is like you'll take the embeddings of each of these words and then you'll average it to predict lugubrious or dissenter word. Like when you have more than 1 words, you have to average the other contexts. Does that make sense?
Yeah. When do you concatenate?
Sorry?
When do you concatenate the embeddings?
When or where? So basically you have an intermediate layer where you're just taking an average of this embeddings. You're not concatenating anything, you're taking the average.
Yeah, but I'm seeing many papers that they do concatenate the embeddings.
Sure, yeah, but here,
I'm just trying to understand when would you concatenate versus averaging? Like what is the program or pros and cons?
you know, you can do concatenation in law. Like we'll see that when we do attention, like in a few, I think next lecture or after, then you'll see when do we do concatenation. We'll cover those. But right now, like there's no concatenation, just this is not it, but we'll see examples of it. So the question for everyone, yeah. Yeah.
Just to clarify what exactly is happening, so we have the context where it's the only, it's a one hot vector. We estimate we get a single embedding VW, right? What happens to the W0 matrix? Are we using the target word and getting?
Yeah. So think of it this way. So what's your end goal? The end goal is that you want to have the embedding matrix Wi and embedding matrix W out. These two trained in a way that it's predicting the same thing. So if you give it like, been feeling, it gives you lugubrious. That's the idea. So how do you learn and whatnot? So think of it, it's like, pulling strings between like different weights and finally, okay, so this is the adjusted weight. So these are the two things that we're trying to learn. No, the objective is to learn the embedding matrices, W input and W output, such that when you give any input word, it gives you the right output word. Right. Yeah, that's a good question. So we'll come to that a little bit later, maybe when we talk about language modeling. But yes, so the question was that we're not encoding any position, but it's in spoken, like in language, position is important, or what does it matter in syntactically. But we'll come to that. That's a good question. Oops. Okay, so skipgrams is easiest way to think about it is just like invert the CBOW task that we just talked about. So we're trying to predict the center word, and now we're given a word and we're trying to predict the surrounding words. Okay, they're according to Mikolov, like either of this works better in certain scenarios, like skipgram works well with small amounts of training data, represents rare words, whereas CBOW several times faster to train, slightly better accuracy for frequent words. So, there's two variants, each has its pros and cons, but the main idea is that when in skipgram here, the task is inverted, now you're trying to, given one word, you're trying to predict the context words. And here, so for example, Y, each of this, so here you're predicting 3 context words. Think of each of them as like individual multinomial distribution on the number of vocabularies, number of words in your vocabulary. So, okay, so segueing on that question, that what do we want to do here? Like how are you actually doing the learning? So again, we're trying to, the whole process of learning happens in learning the weight parameters or the theta. And how many parameters do we have here? So let's say for the input words, if you have like, 100K or 100 word vocabulary, like that's represented by V over here. So these are all the input words, and these, the ones with capital and blue are all your output words. So essentially the parameter of your theta is 2V into H. H is the size of each of the word representation or word vector. Okay, so what we're trying to learn is learn this ideal theta that serves our purpose. Okay, so learning, there's many ways to do it, but gradient descent is the most popular choice. So essentially, you're given T tokens of training data, and you're trying to optimize the objective. Some word, next word, given this word, whatever is your context words. Okay, so this is what you're trying to optimize for, and we basically update our theta parameters by basic gradient descent step, which I'm sure all of you are already very familiar with. And in order to do that, so we need to take a derivative of our objective function. So here, if you recall that the probability of the output word given the input word is we have to do a softmax function, and this is so on the bottom you have this is the softmax function that we need to take the derivative of this guy over here, and how do we do it is the question. So this slide sort of goes through the derivation of log of the softmax function, which I'm pretty sure that most of you have already covered in first year calculus, but let's quickly go over it line by line. So here you have the derivative of, this is your function, and then you're expanding this. So so this basically log division becomes like subtraction here, and this part is obvious, so you take the derivative of log exp cancels out, and then you get the v on the left hand side. On the right hand side, you're trying to take the derivative of log sum exp over here, and then you can do the chain rule to get, this should be like a homework exercise for you to how do you get this from this. Actually, maybe any question like who? So let me ask you a question. So in this guy over here, just this derivative over here, if you want to do the chain rule, what's our z? What should we take as z? Yeah, go ahead. Sorry? So for example, like we can simply take the, so if we take this guy as z, then, VWT, obviously I did this like in grade 8 or something. So, so you can do log z, which should be this, right? So what you're getting is, you're getting this guy in the denominator, okay? Keep this in your mind. And then you can do, if you take dz by this guy, then you should be able to convince yourself, because all the terms except for the term wt becomes a constant, so it just drops out. So you're left with just this term over here, VWT times EXP VWT of, please pardon my handwriting, I shouldn't. Okay, so this is our numerator, and this is, 1 by z, so this is our denominator, right? So you should be able to convince yourself, if you go back here, so probability of word output, WO given word input, if it's this guy, so what we got in the next slide is essentially VW times probability of word output given word input. Any questions? Okay, good. And so this is what we got here. Yes?
So one of the arguments I've heard in regards of why we use different representations for input and output words is that the derivatives are nice. But even though we choose different input and output representations, during learning, they end up being very close to each other. Do you have any other argument as to why we will
do you mean two different representations?
Because we basically consider one embedding when we represent a word as an input token rather than a word, and a
Right.
different representation for when we're considering the word as an output word, right?
So you're learning the embeddings, right? So your representation for the words, they sort of remain the same. So you have still, think about it like, you have a word and you have like a unique identifier to identify that word. So that doesn't change. What's changing is what you're trying to do here. So here the task is that I've given this unique identifier, like, I don't know, whatever, IXCT, whatever. And given this token, I want to predict the next token or the context words, right? But the identification, when you say representation of the words, like there's a unique identifier for each of the tokens to identify. What you're learning is the weight parameters that essentially gets whatever task you're trying to, whatever your objective function is. And in order to do the learning, you're applying stochastic gradient descent, and that's why we take the derivatives and sort of update the weights. So here we're updating the weights. We're not, does that make sense? Like we're not essentially using different representations for, or we're not changing the representation of the IDs of the tokens.
Well, we're learning two vectors for each word, right?
We're learning the weights of, yeah. Oh, okay. So how would you learn, if you have the same matrix, how would you? Well, I mean, I guess I see the question. So maybe that will be more obvious when we do like RNNs and you have like different weight matrices for different inputs and like hidden matrices. So maybe that will make more sense. But I understand the question that why do we need, yeah, it will make more sense then. But yeah, we're not changing the representation, but we'll come to that, okay? All right. Okay, so let's move on. So this slide is essentially what we're talking about, that instead of doing like a one-hot encoding, can we do like, a dense encoding and, or a latent space representation of our word vector, and what does that give us? So for example, like if you want to do cosine similarity matrix, for example, let's say between the words lugubrious and sad, which are semantically sort of close together. But if you just have a one-hot representation, any other word apart from lugubrious is just going to give you 0. Like if you look at the definition of the cosine similarity and this representation, it should be clear to you. But what having this latent space embedding of a word gives us is that it gives us better ways to calculate the semantic similarity of different weights. So after we've learned like this here, the similarity matrix of lugubrious and sad, it gives a high value, like denoting that they're closer together. We can't achieve that using like a basic one-hot encoding. Now, the problem if we want to learn, word representations like this is this, to put it very simply, like if we look at the mathematical intuition is that we've been trying to capture this, like given an output word or the context words, what is the output word, whatever it is. The denominator over here that in the softmax function, where let's say in our running example, we say that we have like 100K examples, right? 100K words. That's our vocabulary size. Now that's, just imagine doing that for every word we're trying to do this softmax. It's computationally infeasible, right? And it's also like, if you think about it, it's a waste of time because, if semantically we know that, like if you're trying to predict the context words for lugubrious, right? So then if you think about words like, I don't know, zebra, rocket, or like maths, maybe maths makes you lugubrious, I don't know why, but anyway, the point is that we shouldn't have to take, all the words in the vocabulary just to do this. We can sort of like sample and take relevant words. So that's one intuition that we can apply in order to make it more computationally feasible. And yeah, so with that intuition, So basically, like here with the running example of lugubrious, we can say that we want to maximize the association of like positive context, like lugubrious or lugubrious feeling, lugubrious tired, that we think like semantically, like, you know, that makes sense. And we want to minimize the association of hallucinated context, essentially like context that has nothing to do with lugubrious or very unlikely, right? So can we do that? And we do that using this technique called negative sampling. Again, the idea of the negative sampling is right now what we're trying to do is that we've looked at a technique and now we're trying to make it more computationally efficient. So we're looking at techniques to make it more computationally efficient. With negative samples, what we do is that we choose a small number of k negative words and we just update the weights for the positive and the negative words, okay? So in practice, like k could be anything between 5 to 20, it works well. But if you think about it, if we do that, the amount of saving is incredible, right? Like, from having to do this for 100k words, all words in the vocabulary, we're just only updating like 0.006% of the weights in the output layer. And this is like the objective function for with this setup where this green one shows that what we're trying to maximize, and on the red you're trying to like, you know, minimize the association of this negative like k samples. Now you can ask question that, oh, how do we pick this k samples? You can, I mean, a simple way would be just you uniformly like sample like k words from a corpus, you know, PW, a corpus probability, or from a corpus. But there are obviously, like every other technique, there are many variants to it. So for example, in this paper, Mimna and Thompson chooses the top k words using a modified unigram probability instead of a uniform unigram probability, which is shown over at the bottom where the corpus probability is raised. Yes? That's exactly what I'm saying, yeah. So you can, basically the main difference, like CW here is the corpus probability. The intuition over here is pretty simple, that like, you know, 1 out of 4 times sample something that is outside like the, like, you know, rare words. So in this way you sample some rare words sometimes instead of picking the top k words all the time or top probable words. But essentially like you can just think of it as simply that we choose k random words. Instead of doing the entire vocabulary, you can just pick k random words, which can be top k words, whatever it is, like, and that should work. Okay, so let's take a different approach now. So then GLOVE or global vectors is an alternate method of obtaining word embeddings. So here, instead of like, you know, doing this for every word, what we'll do is that we'll just do one pass over the entire corpus once and basically populate what you can call as a co-occurrence matrix of the words in the corpus. And what it does is that it's essentially, you know, updates this co-occurrence matrix, which is self-explanatory, like how many times a word has co-occurred with another word. For example, here, like, you know, deep has co-occurred with the word learning one time. In this sentence, I like enjoy deep learning NLP, et cetera, right? So you do this for the entire corpus. And we'll see next that how does it help us to, you know, achieve our purpose of obtaining like good word embeddings. So the intuition over here is that, you know, so far we've been, like, this is the probability that we've been looking for. Like, you know, given some word, what is the probability of another word, like whether it's the next word or whether it's the words in context. So now we're going to represent this probability using this ratio of co-occurrence divided by, you know, number of occurrences of that word. And the whole idea is that the noise of irrelevant words falls apart in the ratio. And this table over here sort of gives you a good example. So let's say you're trying to calculate, you know, the probability of like ice and steam, right? So what you do is that if you look at like here k, we have k like probe words, where here k solid, gas, water, and fashion. Now, if you take the probability of like, you know, each of these probe words given ice, and you know, if it's like, you know, ice is solid, so it should be a little bit, it's higher probability compared to like, let's say fashion, right? So you calculate the pK for ice and steam, and here's the ratio. So in the ratio, if you think about it, that ice, solid given ice should be high probability, semantically speaking. Then probability of solid given steam should be low, right? So if you take the probability of this, this should be high for ice. And if you take that for steam, it should be low. And for irrelevant words like water and fashion, this is just should be close to 1, like it doesn't really matter. So as you can see that from here in the ratio, you're capturing the probability of relevant words using GLOV. So this slide is, it will not be tested. It just basically essentially, this is just the objective function. If you're interested, you can read the paper. But basically, at an intuitive level, if you ask the question that, okay, so, but what about frequent words versus like infrequent words? Are you going to treat them the same? Like there are a lot of words that occur, co-occurrence matrix will be very high, and there will be like some words that are very rare. So essentially, the intuition is that you have, they introduce like a fxij, which is a damping function on the co-occurrence matrix. So it basically normalizes that, like frequent words versus, frequent pairings versus rare pairings. But yeah, I mean, this is not going to be tested. You can read the paper if you're interested to know more about this, or we can also like talk offline if you have any questions. All right, so now let's talk about evaluation. So now that like we have looked at some ways to like, get word embeddings, but how do we know that which one is better or which one is worse? How do you evaluate this embeddings? So I mean, this slide, like, the benchmark here, so essentially the idea is that we've been moving towards more standardized benchmarking in NLP. So before, maybe it used to be like intrinsic evaluation where like you just cherry pick some samples and that gave really good results and you just present that. But now there's more systematic way of testing the efficacy of this word embeddings. So superglue and glue are like two, I'd say old by now benchmarks where you have a bunch of tasks and you can like, use this embeddings to measure the performance qualitatively on those tasks based on the word embeddings. That gives you like a qualitative empirical result of how well the word embeddings are doing as, downstream tasks. As I said that these are a little bit dated now, but I really encourage you to like take a look at the tasks, which I think Glue and Superglue neatly, lists some of the main NLP questions or tasks that are very relevant. So you can have a good idea of what are the kind of, for example, machine translation, which we'll be doing in next few lectures is one of the tasks, but you have a lot more other NLP tasks which are relevant, right? Like word ambiguity detection and things like that. So take a look at these two benchmarks for an idea or, growing an understanding of what are the problems that, are important or. All right, so next I'm going to move into some of the linguistic regularities or observations in vector space. And yes, so knowing very well Gerald's position on vector space, the linguistic regularities, like this was again, I mean, there's a historical background to this, but in the current like zeitgeist, so this captured a lot of attention, which was basically like, after the work to Vec paper, where like, Skip Drum's the embedding sort of captured this linguistic regularities in vector space. So just quickly go through this example that you can see this regularities between like, the capital cities and you see this between like, verb, adverbs, and like, qualifiers like strong, stronger, strongest, and things like that. And this kind of regularities like is very, so here we can see that even it expands to like semantic regularities like, city minus country plus another country gives you the capital of that country, things like that, even through like hypernomes and like shirt is to clothing is to chair is to furniture, and I guess the most famous queen minus king equals to woman minus man. So the vector space of this learned word embeddings shows this kind of regularities, which are very helpful in downstream NLP tasks. And this goes without saying that, you know, the training, what is training? Whatever we're learning from the input. So obviously, like, the input matters. So this slide, essentially, this work showcases essentially what is, I think, obvious, that if you train word embeddings, let's say, on electronic health records or biomedical you know, papers, then that train embeddings will do better than, let's say, generic data in capturing medical terms better. So this paper shows that, like, you know, the importance of in-domain data, and basically, like, you know, as you can see, that it captures medically relevant word embeddings better than, let's say, other word embeddings trained using generic data like Google News corpus or something. And so if that is the case, then one thing that we cannot, we must gloss over is, what about the existing biases in the input data that we use to train our models? So that means that if this is the case, that, you know, whatever you're training your data on captures the underlying notion of those data. So if we do train our embeddings using existing data, and existing data have biases, then that should be captured in the model too. And next few slides will basically talk about, like, biases in you know, generic embeddings. By the way, like, by this time, like, there's a lot of, usually, like, a lot of precautions taken and a lot of techniques applied to sort of counteract these biases. But from a pedagogical sense, it's important for you to understand or see, like, how or what, like, this kind of biases may show. So this is a very highly talked about paper where it showed that, you know, basically, like, you know, man is to computer programmer as woman is to homemaker is sort of the semantic analogy this vector embedding space gave rise to when it was trained on some generic data. So pictorially, like, think of this as the x-axis is like the gender axis, where the right side is associates with he and the left side associates with she. And this y-axis is the gender neutrality line, where the bottom parts are like gender neutral words, whereas the top words are these are gender specific words, and the top words are gender neutral words. To exemplify, let's say brilliant is a gender neutral word, right? Whereas brothers is a gender specific word. So when you say brothers, it should associate with he. So as you can see that over here, like, the problem is that, you know, certain words are more biased towards the gender he, and certain words are, which sort of propagates societal stereotypes, right? Yeah, so for example, like this, that man is more likely to be a programmer, where woman is more associated with being a homemaker. And you can read the paper. There should be a link on the website. But these are some extreme she and extreme he examples, which sort of cherry picks the extreme examples. Like, he is associated with maestro, a protege, and all the good qualities, whereas she is associated with homemaker, nurse, receptionist, and things like that. And so how can we sort of rectify this? Again, there's a lot of newer methods, but here we're going to talk about a very simple method called hard debiasing. So if you want to do this, let's say what you can do is that you can separate words that are gender definitional, and then words that are should be gender neutral, which are in blue. And the idea is to move these gender neutral words away from the gender subspace. And the way you can do it is that you can subtract the gender subspace from these gender neutral words. So if you do it rightly, then the goal is that you want this collapse on this, like, you know, like on this axis, where it's neither he or neither she. That's the goal. And yeah, so hard debiasing actually achieves this goal, like where you're like, the general neutral words are collapsed into a neutral axis where it's neither he or neither she, which we want to have. Now remember that, again, there are certain gender definitional words that we want to show bias. For example, if it's a brother or if it's a sister, we want them to have that bias. Here, so essentially doing hard debiasing like this achieves the desiderata that, we have the stereotypical analogies which are suppressed by the green line, but the appropriate analogies like, he, brother, she, these are maintained. All right, so with that, let's move on to neural language models, and for giving like introduction or just to segue into it, let's talk about trigram models. So far what we've talked about in the word embedding space, we've talked about prediction of words given another word, right? And now we're going to switch gears and think about language modeling. So what is the task of language modeling? So the language modeling task is that, like, you're given a word or preceding words and you're trying to find the probability of the next word. And here we can see that, so with a trigram model, so far we're, with a trigram model means that you have like given two words and you're trying to predict, instead of predicting a word, we're gonna predict a probability distribution, PT over here. And on the left-hand side, you can see that what we have been sort of, like if you have like an MLP, what we're trying to do, we're just trying to predict the next word. But here we have like a probability distribution that's coming from like the preceding two words. If you think about it, that we can basically have a very vanilla kind of language model where you're given two words and you're always predicting the next word from this probability distribution. So let's say if you're given these two words, two writers, and you just pick where, and then you feed that highest probability word into the next iteration where you're predicting the next word. Now you can always ask that, why are we picking the where? What if it was like instead of two writers, we're approaching it could be two writers, begin, closing in, or some other iterations? So that's a good question. So we'll cover that in the decoding part of translation. But here what we're doing is, like, you can think of it as greedy decoding, where we're just picking the most probable word out of the probability distribution. Yeah, so basically in this way, if you can continue doing this, and then you can basically, this is a very vanilla language model. And how do you train such a language model? Again, you can do a basic, like, a stochastic gradient descent approach where you randomly choose a batch and then propagate the words to the current model, obtain the word likelihoods, and then backpropagate the loss, and then update your weights, and so on. So pictorially, I think you've covered in the previous lecture, Sean covered the entropy. So basically, we need an objective for training, and historically, we use cross-entropy loss as our training objective. So as you know that, like, we want to minimize entropy, because minimizing entropy means minimizing less uncertainty with minimizing entropy. And here you have the minus log probability of PMC is your probability of the corpus, which is basically equivalent to maximizing your log probability of your corpus given a model M. And yeah, and this term basically shows your cost function. And this slide essentially shows that how would you basically backpropagate in order to update your weights. Now let's close over here for today's lecture, and we'll do RNNs and LSTMs in next lecture. Thanks a lot.